Welcome to this video on polarity. In the last two videos, we've been looking at how atoms share electrons to get a full outer shell. But sometimes those electrons spend more time around one atom than others. When these negatively charged electrons do this, they mean that one side of the molecule can become more negatively charged than the other side of the molecule. This imbalance in charge is called polarity. That's what we're going to look at today. Before we delve into it though, you need to understand a new term called electronegativity. Electronegativity just means the ability of one of these atoms to pull at a negative charge, like an electron. And this is primarily dictated by the number of protons. So for example, if we compare hydrogen to fluorine, fluorine has 9 protons in it. It's number 9 in the periodic table. Whereas hydrogen only has 1 proton. And because positive protons are what do the pulling on a negative charge, fluorine is going to be pulling harder than hydrogen is. So fluorine is more electronegative. Generally speaking, going from left to right, the atoms on the right-hand side are more electronegative than the atoms on the left-hand side. Apart from all of these noble gases down the right-hand side, they have full outer shells and they're not interested. So fluorine is the most electronegative atom. Then oxygen, then nitrogen. And these are the ones that are going to be most interesting to us, especially when compared to hydrogen, which is not very electronegative at all. One further thing which is less important but also good to know is that atoms at the top of the periodic table are more electronegative than atoms at the bottom of the periodic table. And that's because atoms at the bottom, this bottom row, has 7 layers of electron shells. That's 7 layers of negative charge. So all of that negative charge is going to start to repel other negative charges, so it makes them less electronegative. However, we often only look at atoms up the top of the periodic table anyway, so your key message is going to be remembering that atoms on the right-hand side, apart from these noble gases, are more electronegative than atoms on the left-hand side. So let's look at how this affects molecules. If we have H2, for example, that's made up of a hydrogen sharing an electron with another hydrogen. And they have 1 proton each. Seems very simple. If we compare that though to hydrogen sharing an atom with fluorine, fluorine is much more electronegative. It has 9 protons compared to hydrogen's 1. Therefore, the electrons that they share in a bond are going to be much more attracted to fluorine than they will be to the hydrogen. So although we often draw electrons as these little dots, what they really are clouds whizzing around each of the atoms, spending time around each one in turn. And with hydrogen, because they're equally electronegative, they're going to spend an equal amount of time around each one. Compared to hydrogen and fluorine, where fluorine is much more electronegative. So the electrons that they share are going to spend much more time around the fluorine atom than they will the hydrogen atom, because they're more attracted to fluorine. This means that HF is a polar molecule. The negative electrons are spending more time around fluorine, so fluorine's going to be more negative. That means hydrogen is going to be more positive. Compared to the two at the top, where the electrons are going to spend an equal amount of time around each hydrogen atom. So we call this top one a non-polar bond. So the electron cloud is evenly shared between the atoms in a bond. Compared with HF, which is a polar bond, because the electron cloud spends a greater amount of time around one end of the molecule, in this case the fluorine end. And we draw this with a delta negative to show the negative side of the molecule where the electrons are spending most of their time, and a delta positive to show where the electrons are spending the least amount of their time, the slightly more positively charged side of the atom. Let's look at a few more examples now. So when we look at each of the Lewis diagrams, we can figure out where the electrons are going to spend most of their amount of time. But we're going to do one more thing. We're also going to compare the electronegativity of oxygens, hydrogens, and carbons. Carbon we can think of as neutral, hydrogen is very weak, oxygen is very strong. And you'll see that by looking at your periodic table. So first of all, strong oxygen is going to pull at the electrons, meaning that the electrons are going to spend more time on the right-hand side of this molecule. Whereas in carbon dioxide, oxygens are going to balance each other out. So the electrons are going to spend a similar amount of time on each side. And then when we look at H2O, we look at water, oxygen is stronger than hydrogen. So the oxygen is going to hog a lot of the negative electrons, leaving the hydrogens more positive. So we can label these. The hydrogens in this case are going to be slightly more positive and the oxygen slightly more negative, meaning it's a polar bond. Whereas with CO2, it's a non-polar bond because the electrons spend a similar amount of time right across the atom. And again, we have slightly negative with oxygen and slightly positive with each of the hydrogens in water, making it a polar bond. So here's what you need to know. You need to know that electronegativity is an atom's ability to attract negative charge. And with what we're concerned with, that means attracting electrons in the bond. And that's going to increase from left to right in your periodic table, with fluorine being the strongest, then oxygen, then nitrogen, and so on. We also need to know that polar molecules are when the electron cloud spends a greater amount of time at one end of the molecule. Like in water here, the oxygen is going to hog the electrons most of the time. So that's going to be delta negative, slightly negative, whereas each of the hydrogens are going to be left slightly positive. They're losing out on their electrons, so all they've got is a positive proton left out on the side. And finally, non-polar molecules are where the electron cloud is evenly shared between atoms in a bond. Let's look at a question now. Here we've got the three-dimensional drawing of two molecules. We need to circle the word that best describes the polarity of each of these two molecules. So if we look at CBr4, we can figure out without even looking at our periodic table that Br is going to have the same electronegativity as all the other Brs. Therefore, they're all going to be equally pulling on the electrons. So the electrons wouldn't spend more time around one Br compared to the other. They're the same. So therefore, CBr4 must be non-polar. But when we compare that to Br attached to a carbon, which has 3 hydrogens on the other side, if we look at our periodic table, we'll see Br is more electronegative than hydrogen. Therefore, the electrons are going to spend more time around Br than they are about hydrogen. So that means it must be a polar molecule. So for the first one, we want to say that all of the bromine atoms have the same electronegativity, therefore they'll evenly be pulling the electrons in all directions. Whereas with this one, the bromine is more electronegative than hydrogen, and therefore the electrons are going to be pulled away from hydrogens up towards the bromine end. And that is how we get some polar atoms and some non-polar atoms, using the idea of electronegativity.